pleasure to welcome Robin Walters, who will be talking about symmetry in neural network parameters and non-linearities. Yeah, thank you.
Okay, thank you very much for the invitation. It's a pleasure to talk to you. So this talk is about symmetry in neural networks. So symmetry in neural networks has been like a blossoming field of late. So using equivariance and various symmetry to improve the performance of neural networks since maybe around 2016. But it's really like come into its own of late. So the work that I'm doing, so for that reason, people may be sort of familiar with this kind of intersection previously, but the work I'm going to be talking about is really in a very different direction. So I'm focusing not on the symmetry of data, so like the inputs and outputs of the function. I'm looking at the symmetry of the neural network architecture itself, of the parameter space, and trying to exploit that to improve sort of the optimization of neural networks. So I'll present in some relationship to that. So I'll start with some introduction of symmetry and how we talk about it and how it intersects with deep learning. And then I'll specifically talk about the symmetry I'm interested in, which is the symmetry of neural network parameters. And then I will show you how to use symmetry to do model compression. Essentially, symmetry corresponds to some kind of redundancy in the parameter space. And so model compression often works by eliminating redundancy. So awareness of that symmetry lets us produce smaller models. And then I'm going to talk about the interaction between this sort of group actions in the parameter space and gradient descent, which is very interesting. And then lastly, I'm going to talk about how you can sort of use those group actions and the interaction with gradient descent to actually accelerate the convergence of gradient descent for optimizing neural networks. So I guess I'm supposed to go for 45 or 50 minutes with questions at the end, but you can also feel free to interrupt me in the middle. These are my collaborators. So this talk is based on two works, which you can see on the archive links. So Iordan, Ganev, and Twan van Laarhoven are at the University of Radboud. Bo Zhao and Rose Yu are at UCSD, and Nima Dehmamy is at IBM Research. Okay, so let me first just talk about like the language of symmetry, which is the language of group theory and representation theory. So we represent symmetry as a group. It's a set of transformations that leave something in the space invariant. So here, for example, I'm showing the dihedral group of order 6. This is the set of symmetries with an equilateral triangle. There are 3 rotational ones, or really 3 rotational ones and 3 reflectional symmetries. And it's a closed system. So if I compose any of these transformations, I end up with another one. So another important group, which is a matrix group, is the general linear group. So these are just n by n invertible matrices. And obviously, if I multiply any 2 invertible matrices, I get another invertible matrix. And then importantly in this talk, there's also the orthogonal group. So these are invertible matrices whose inverse is equal to their transpose. So matrices that preserve the Euclidean norm. Okay, so an important distinction between groups, which are the abstract representations of symmetry, really just contain the elements and the multiplication table and the representations of those groups. So I'm a representation theorist. So to me, that's the special part of groups is their representation. And so basically what a representation is it sends each abstract element of a group to an n by n matrix, where the multiplication of those matrices reflects the multiplication table of the group. So in this example, I have the C4 cyclic symmetry group, right, which contains 4 elements and has the multiplication table that when you take the generator to the 4th power, you get back to the identity. And a very natural representation of this group, in fact, I guess it's called the standard representation maybe, is by 2 by 2 rotation matrices, right, where we rotate by 90 degrees, right? And you can exactly see that if I take this matrix to the 4th power, I'm going to get the identity matrix. And that's why this is a representation of that symmetry group. But what's important is if you've only ever thought about matrix groups, it's important to realize that any group has many different representations. by exploiting the different representations of that group, that's something that can be very useful later, we'll see in deep learning. So for example, in this group, I could also have a representation by 4x4 matrices where I am representing this sort of four-fold symmetry by permutations of the four vertices of the square, right? So we just send the standard basis elements of R4 in a cyclic group. And if I take this matrix to the fourth power, I also get back to the identity. So now I'll just say for a minute, so this is like where, you know, there've been maybe like 100 or 200 papers in the last like 5 or 6 years on sort of equivariant neural networks, which is the typical way that symmetry, group theory, and representation theory are used these days in deep learning. So this is not the main focus of my talk, but I'll just talk about this in contrast to what I'm doing. So for an equivariant function, f from x to y, okay, given an input x, we say that this function is equivariant if when I transform the input by some element g according to the way g acts on that input space, then what I get out is the same output, but I transformed by the corresponding transformation in the output space. So this image, I think, makes it clear. So this F is a machine learning example. It's doing a segmentation of the objects in this image. And this segmentation map is equivariant with respect to rotations. So if I rotate the pixels in the input image and then apply the segmentation process, that is the same thing as if I first applied the segmentation process and then applied the rotation. So it's realizing that this function f that I want to model has this symmetry property that allows us to exploit the symmetry in deep learning. Essentially what we do is, instead of trying to learn this function using a standard unconstrained neural network, we impose some constraints on our space of neural networks, and we impose exactly the symmetry constraints that we want to see. So we're looking at a model class of equivariant functions, and we're trying to perform optimization within that model class. So that represents a reparameterized subspace within the original space of neural networks that enforces that symmetry. And what I want you to focus on for the point of this talk is, where is the representation of the group, right? So here, the thing that the group is transforming, so the thing that I am seeing symmetries of, is the input variable x. The output variable, so that's f theta of x, is getting transformed by this row out, right? And the symmetry is of the mapping f theta in terms of its inputs and outputs, right? So it's x, y, the hidden spaces, and the function in terms of those that has the symmetry. Okay, so in this talk instead, right, it's not the x and the y and h that I'm going to be acting on, it's the theta, it's the parameters of the network. And so I'll denote the parameters by theta, or occasionally I'll break theta into the layers of the network, and I'll try to use consistently the w, or sorry, v for the space of parameters of the neural network. Okay, so let me talk specifically now about what that looks like. So here is my space of neural networks. So this is just like a basic MLP structure. I'm gonna play pretty fast and loose with bias in this talk. So usually when I want to structure bias into a neural network, instead of explicitly writing wx plus b, I'll simply assume homogeneous coordinates, which means that the bias is just a column inside w1, and there's an additional 1 on all of these feature vectors that corresponds to homogeneous coordinates. Okay, so this is my model class with L layers and weights W, right? And it contains these functions f theta parameterized by theta. Okay, and so this vector theta is the collection, or the tuple, of these WL matrices, and this is my space of parameters, right? So essentially, it's just a large vector space of dimension d1 times m plus d1 times d2 all the way through n times dl. So it's just a very large real vector space, and that's my parameter space. Okay, and so the mapping that I'm looking at, right, is that what we have is a map from a given set of parameters to the function f theta that goes from Rm to Rn, that is parameterized by those parameters, right? And what I want to look at explicitly in this function is to note that this function is not a one-to-one function, right? So I can have two different sets of parameters that lead to exactly the same neural network. So that means that there's a high amount of redundancy in the parameterization space of FV. So this is kind of related to the when people talk about interpolating functions or the over-parameterized regime of function fitting. But usually that's meant in a more continuous sense. And here I mean like literally I get exactly the same function f theta for different values of theta. So how can we use symmetry to sort of see this redundancy? So what I'm assuming is that I have access to some group of transformations and some representation that lets that group act on V, my parameter space. Okay. And I say that I have symmetries of my parameter space if the transformations of my parameters theta by that group element G leads me to the same function F. And later I'll give like a weaker version of this definition. So this is maybe having symmetries in the strong sense. And as I said, these both two different sets of parameters lead to having exactly the same model. And what's different about that than sort of the equivariant learning or geometric deep learning case is that here I'm not assuming G is acting on X or Y, or that F theta has any symmetry at all, right? Which is an important constraint of that setting, right? You have to have a special F and a special X and a special G. This analysis really applies to any function. It's really about the model class. So I'm going to give an example. So here's an example just to show like how prevalent and common this is. So I'm going to take a completely standard class. So I'm just going to assume like a basic feed-forward network with no skip connections, no convolutions, just a multi-layer perceptron. And I'm going to assume that the non-linearity that's used in these layers is pointwise ReLU. So just applying the ReLU function to every component of the vector in each hidden layer, right? Then this model class already has the symmetry given by this very large group. So basically what you have is you have these permutation, you have a big product of things, but you have permutations on the hidden layers, and you have positive rescalings of the neurons. So I'm going to denote elements of these permutation factors as SI. So these permute the neurons in the hidden layers. And I will denote by DI these positive diagonal rescaling matrices. So notice, well, I guess I'll get to in a second. So here's the definition for this for rho V, which is the group action on the hidden layers, right? And basically what I'm doing is changing the basis of the hidden layers. And since the basis of the hidden layers was in some sense arbitrary, that will not change the output function as long as I am consistent and I change the basis both on the outputs to the previous layer and on the inputs to the next layer, then they will cancel out. Okay, so concretely, it is the non-linearities, like it's in my title, symmetries, the non-linearity. So it is the non-linearity that I choose and the symmetries of it that have to be compatible. So here, S is a permutation matrix and is switching Z1 and Z2, the first two components. I have a hidden feature here of size 3, right? And what I want you to notice is if I first switch Z1 and Z2, and then I apply ReLU to each component, right? That is the same thing as if I had first applied ReLU and then switched the components. And that's just because ReLU acts identically on all components of the vector. So it commutes with permutations. Okay, and similarly, this positive rescaling, right? So ReLU is 0 on negative entries and the identity on positive entries. So if I rescale factors by a positive number, right, then that's just going to leave 0 as 0. Or if I'm on the identity side, then it will just scale the identity, which means I can commute positive rescalings with ReLU, right? Notice, like, if R1 was a negative number, then this commutativity relation would not hold, since it might flip Z1 into a negative number, in which case I wouldn't get the same thing. Okay, so now let us, so I'll just show what's going to happen with the linear layers here and prove actually this claim that this is a symmetry of the neural network. Okay, so here's the action that I defined before. So I am pre-composing and post-composing each layer with these change of basis operations given by permutations S and rescalings D, right? And so notice the D2 and the D2 inverse and the S2 inverse and the S2 want to cancel, but there's a ReLU in between, right? And since we just showed that these group operations commute with ReLU, right, I can move these inverses over to the other side past the ReLU, and similarly with the next layer, and now all these things can cancel. And that gives me exactly the model that I had originally, right? And that was my definition for having symmetries in the latent space. Okay, so that's the ReLU example, and this is already a pretty big symmetry group, right? The permutation group of size D is size D factorial. So if I hit a layer of size 128, then that's 128 factorial symmetries and 128 dimensional continuous symmetry rescaling space just for that layer. So that's a lot of redundancy. So what I am going to spend more of this talk on is the example of a radial neural network, both because it's a bit natural for me coming from the space of studying equivariant neural networks, and also because we wanted to ask ourselves, given like that we have this perspective of looking for symmetries in the parameter space, what is an example of a nonlinearity that would really have like a lot of symmetries? So we introduced this radial rescaling function. So the way this radial rescaling function works is I first choose any function I want from R to R. And then my nonlinearity on a layer Rn to a layer Rn is going to be given by taking the vector v and renormalizing it. So all I do is change the length of v by this scalar h that depends on the norm of v. So these sort of radial nonlinearities first came up in the context of rotationally equivariant functions. So if you're trying to preserve rotational symmetry using a neural network, then the standard necessary but not sufficient sufficient but not necessary condition that people impose is that all the layers be equivariant. And if you ask, what does it mean to be equivariant to rotations for nonlinearity, right, then essentially means the nonlinearity needs to do the same thing no matter what direction I point in, and that leads you to having a radial rescaling function for your nonlinearity. So you see these in capsule nets and also E2CNN. So now, similarly to the ReLU example, right, we can ask, right, now that I have suggested that I'm using this radial rescaling nonlinearity, what symmetries do I have, right? So like I kind of gave it away, right, by saying that we're maximizing symmetry, and this comes from the rotational case, but it's this orthogonal group of size di acting on each hidden layer, and that's my symmetry group, since those are rotations in the RD space. And so we define the action. This is really actually the same definition that we had in the ReLU example, except now I'm acting by orthogonal change of basis matrices instead of rescaling and permutation matrices. So this is, I just have this one like change of the slide, right? So I've written in this very sort of simple way. And if you want to just imagine you have no bias, then this is very fine. If you want to technically see like, what is this action? If I also have that the bias is built in as the first column of my matrix, right? Then the GI acting on the outputs of each layer is going to transform all of the columns, whereas acting on the inputs, you act on the linear part, but the first column representing the bias, the input to that would be unaffected. So this is technically what you would write down if you wanted to include the bias explicitly. Okay, so now I'll just prove that this is the symmetry group, and the proof is pretty much the same as before, but the key is just noting that if this is my radial rescaling function, then the radial rescaling function commutes with orthogonal transformations, right? So if I take this group action G on my input and HD is a radial rescaling function, then I can evaluate it like this. And since orthogonal transformations preserve the norm of vectors, so I'm denoting norm with single bars here, then the norm of GZ is the same as the norm of Z. And so I actually could just get one G here, which I can pull out since this is linear and it's a scalar. And so what I get is that the orthogonal group commutes with the radial rescaling functions. And sort of just, going back to this proof, we basically now have exactly the same proof. since really the only steps that we had to do to make this work was to pull the action through the nonlinearity. Okay, so those are the kinds these are two examples. Those are the kinds of symmetries that I'm talking about. I will add one more example of another type of neural network and another symmetry that it has in its parameter space later, but these are good enough, I think, to get going. Okay, so now that I think it's interesting on its own to think about redundancy in and symmetry in parameter space, but I want to show that you can actually realize some practical advantages for things people want to do with neural networks using that. Okay, so one important area, I should really have like a motivation slide here just talking about model compression in case you don't know what it is or why it's important. But as you probably know, neural networks have gotten very large, right? So they have these language models, right, which are now, I think, in the hundreds of billions of parameters, right? And explicitly evaluating these models, although it can be done very fast in very large data centers, is very compute intensive, right? So like a lot of money that large corporations spend these days is essentially to run data centers to evaluate these models. So if you can take a model and make it smaller, fewer parameters, less memory, less compute time, then you can evaluate many more models using the same, many more steps of inference independently using the same hardware, and you can literally save money. You can save energy, you can have a smaller carbon footprint, you can run on less expensive hardware, and so forth, and realize all those advantages. So how am I going to use symmetry to do this? So this model compression algorithm is for the radial rescaling case. So that's the case in which I have a lot of symmetry in my parameter space. And here's the idea. So let f theta be a neural network with radial rescaling activations, and denote the size of the layers by dimension of the layers by d0 through dl, where d0 is my input and dl is my output, and d1 through dl minus 1 are the hidden layers. Then I can't change d0 or dl because those are the inputs and outputs to my function. I didn't choose them. But I can hope to reduce the dimension of the hidden layers of my network. So what I do is I step through recursively from the beginning to end of my network, and I define these di reduced to either be di itself or the size of the previous layer plus 1, whichever is smaller. And so as you go through recursively, you will shrink the di in your network. And this is going to be the size. So here's an example. It's like admittedly kind of an extreme example to favor our case. But this is the size of the network that we will get after performing model compression. Okay, so here's our theorem. So if you have this model with these radial rescaling functions, then there is an algorithm that gives you a reduced network with this much smaller size. And moreover, this compression is lossless. So model compression, like other compression algorithms, a lot of people would feel fine if the outputs were like within 1%, if you were able to get like, you know, a 50% reduction in model size. But in this case, because this is based on the actual precise redundancy inside the parameter space, since it's based on actually a group action that preserves the function, here we get a lossless compression algorithm. So the reduced model is exactly the same as the original model. Okay, and can
I ask a short question?
Absolutely. And
So
who's
this
asking?
only-
I'm not sure.
Here it says it's only less or equal. So can it be that there's actually no compression?
Yeah, although, so like, for example, like basically this reduction is once you've reduced, right? I guess it's like idempotent. So once you reduce, if you reduced again, it would be the same values. So if you started with sizes that were already reduced, then applying reduction wouldn't get you anywhere.
My point is this statement, I mean, I could just return the same network and it would satisfy what this theorem claims.
Right. So I guess, okay. So like in some sense, the theorem, well, that's not, so this is, so maybe the theorem is stated a little informally, but this is part of the theorem. The DI red are defined here. I'm just commenting that they are in fact smaller. Okay. Yeah.
So it shows the okay. Yeah.
Yeah. So we will get this DI red. Okay. Okay. So so the proof is cool. So the proof is going to use the symmetries, and it's also going to use QR decomposition, which is always fun. But the idea is basically, right, that I have this freedom of this orthogonal group at change of basis action in the hidden layers, right? And so can I take the network you gave me and apply some rotation in this OD, right? Some orthogonal transformation that rotates the hidden layers so that I don't need as many neurons to represent those functions, right? So just to remind you, the QR decomposition, if you haven't seen it in a while, right? Given some n by m matrix, right, I can decompose that as an n by n change of basis matrix and an n by m matrix R, right? So basically what I'm doing is I'm finding, so one way to do this is the Gram-Schmidt procedure. Basically, I'm finding an orthogonal basis of Rn using the columns of this matrix, and then R gives the coordinates of the original matrix. If I follow the Gram-Schmidt procedure, right, for example, then I'll have an upper triangular matrix. Okay, so what we're going to do is we're going to upgrade this sort of orthogonal group to our product of orthogonal groups that's acting on all the layers. Okay, so basically we're going to find a tuple of orthogonal elements in our product of orthogonal groups and a tuple of upper triangular matrices in the parameter space, so that the I have essentially a simultaneous QR decomposition of the weight matrices of all of the layers of my neural network. And so I'll specifically give the algorithm in a second, but I do not mean just independently QR decomposing each network. I mean something more specific, because remember, right, that the group action, so this rho V of G acting on the R, right, this is the action that we defined a second ago, right? Let me go back to it, right? This is this action, right? So this can't just be the QR decomposition of each layer, because each orthogonal group is acting simultaneously on the previous and next layer, right? So you have to do it all simultaneously. The actions are intertwined, or not intertwined, are linked to multiple layers. Okay, so so the procedure is that you go iteratively from beginning to end of your network, right? So starting at the beginning, you perform a QR decomposition and you factor this Q out of the first layer of your network, giving you this QI. Now, because the Q commutes with, so what I've already done, right, is I've already done some simplification to the first layer of my network, because I've replaced it with this upper triangular matrix, whereas originally I had a full matrix, right? And this QI can commute with the nonlinearity. That means I would get the same network if I detach the Q from this layer, pass it through the nonlinearity, and apply it to the inputs of the next layer. So that's what I do, right? And then having done that, I update that layer, and then I start over and I work all the way through until all of the weight matrices of my network are now all in this upper triangular form. So this is the sort of iterative QR decomposition algorithm for a neural network. So visually, I'll just show how this works. Now, in this case, I'm going to reduce, I'm not including a bias. So if you don't include the bias, then you get, it's kind of a degenerate case, and you just get without the +1 step. So here I have input dimension 1. So I'm going to be able to reduce to 1, 1, 1 in this case. So the bias is actually quite useful and important here, but I can demonstrate the algorithm very simply in this case. So we're going to start here, and we're going to do a QR decomposition. So I factor this, this 4x1 matrix to give me a 4x4 Q, okay, and a 4x1 R matrix, which is upper triangular, right? Now what I do is this Q can move through my radial rescaling function and act on the inputs to the next layer. So I do that. So there it goes, moving over. It would be a little visually easier to see if the order of, so matrix multiplication kind of goes right to left, but the commutative diagram goes left to right. So that's why popping from the output to the input over here looks like it's flipping sides, but it's really just shifting through the sigma. Okay, and then I act. And so that gives me this matrix. And remember, all of these steps are preserving the forward function of the network. Okay, and now I notice the following thing. So this is where the model compression comes in, right? Because the input to this matrix was size 1 and the output was size 4, this is a rank 1 matrix, which is why my one column that's upper triangular really just has this one entry with all these zeros. So that means the weights here are all 0, right? That means these inputs are meaningless, and I can get rid of them. And consequently, I can get rid of all the outputs that came from that. And now this is my new truncated reduced network. Now I can repeat this procedure. So I perform QR decomposition on this layer. I move the Q's through the sigma to the other side. Essentially, I'm using the group action, the symmetries, the parameter space that we've proposed. I multiply through, which just updates that matrix. I notice that I have these zeros now in the previous layer, and so I can get rid of them. So in this kind of toy case, this is how the model compression algorithm works using the symmetries of the parameter space. Okay, so that's the idea. So now what I want to talk about, and also be a segue into the next section, is how does model compression here, and this specifically these group actions in the parameter space, interact with gradient descent or optimization of the model? So in some sense, this is a bit extra because even if you just had a good model compression algorithm, you don't necessarily need to ask the question about how it interacts with training the model. Like in practice and industry, people do a lot more evaluating models than training them. And so most of the time, what you want for model, like the #1 goal of model compression is smaller models at inference time. So if I can just train my model and then compress it losslessly, I'm already pretty happy. But you could ask for more. You could ask, maybe I could even save time training if I would be allowed to perform this model compression before I train. Then I have a much smaller model to train in the first place. So that's the dream. And as you'll see, that's not what we get. But it's okay. It's still kind of interesting. So just to fix some notation, so some people call this the loss function. I'm going to call it a cost function, which just compares the output of my model to the true value. And I will reserve the term loss function for a function which, given some fixed data samples S, maps parameters to the final loss value. So this is the loss function in the sense of the gradient. So it's the gradient of this function with which we do gradient descent. Okay, and thinking now about the loss function, another way to think about parameter space symmetries is they are invariances of the loss function. So in the way we were talking about equivariant and invariant functions earlier, here it's not the task function which is invariant, but rather the loss function which is invariant with respect to the parameters. Okay, and just to fix some notation, the gradient descent map with learning rate eta, I'm going to denote by gamma. Okay, so now like a little lemma. So how are these group actions, these transformations of the parameters, going to interact with gradient descent? So I'm going to step back for a sec and take a slightly broader view. So assume phi is any linear transformation of parameters, not necessarily an invertible matrix, as is the case when we're considering a group action. And suppose that we have a loss function, which is invariant with respect to that transformation of the parameters. Then what can we say? So you can compute, right, that this phi also acts on the gradient of the loss function, and it acts by the transpose. So in general, if I transform the parameters under a transformation that preserves the loss, the gradient is changed. So that's very important. Okay, but in the case of radial rescaling, right, our phi is an orthogonal transformation. And for the orthogonal transformation, right, phi t and phi is the identity. So applying phi to both sides of this equation, I essentially have a kind of equivariance for the gradient, which translates precisely into equivariance for gradient descent. So what that's saying is that if I have a transformation which preserves the loss function, then that transformation commutes with gradient descent. I can do it either before or after doing a step of gradient descent. And that's what I have in this radial rescaling case. So that's looking pretty good for the question about whether I can perform model compression before or after. But as you'll see, there's a problem. Okay, so the problem is this truncation step. So the problem is when I don't just perform a group action, I also get rid of like the zeros that I rotated away and use a smaller network at the end of the day. So let's let gamma be gradient descent on the full parameter space and gamma reduced be gradient descent on the reduced parameter space after performing model compression. Okay, let W equals G times R be the QR decomposition that we showed a minute ago. And I'll denote by R upper red, this is the compressed model where I chop off all the zeros as I go. Okay, then we have the following result. So I have gamma to the K, so this is K steps of gradient descent. And in this case, because W is a G transformed version of R, in fact, we know that this action commutes with gradient descent. And so we know that actually, if I do full gradient descent on R and full gradient descent on the original network W, they will stay related by this group transformation. However, right, once I remove all of those zeros, so that means that I've stopped performing gradient descent on those zeros, right? Even though I've set them to be 0 and they don't have any impact on the loss function, if you continue to perform gradient descent with leaving the, like after performing compression, but leaving the zeros there, right? Changing those values from 0 to some other value could affect the loss. And thus, sorry about notifications. I'll disable them if it keeps popping up. So thus, if I don't perform a form of projected gradient descent in which I explicitly re-zero out the entries that I have eliminated, then I will diverge from this reduced space. So that means that the model compression algorithm, essentially performing gradient descent on the reduced model is equivalent to performing a form of projected gradient descent on the original model. So on the one hand, that's a disappointment because it says I can't just perform model compression before I do training and expect to get exactly the same thing. But it is kind of interesting because we can explicitly say what the difference between the optimization procedures of the original model and the reduced model are, which I think is interesting. And this leads to the following thing. So, so if that's lemons, this is the lemonade. So if we found that these group transformations aren't exactly preserving the gradient, right? Can I use that in some way to accelerate gradient descent? So here what we're proposing is a modification of the gradient descent algorithm that is aware of and takes advantage of symmetries in the parameter space. And here's the motivation, right? So, so this is obviously a large area of research. I'm sure there's people in the audience who think about ways to improve upon gradient descent, but there are several well-known problems with stochastic discrete gradient descent algorithms, right? Namely, right, when you have certain sort of skewed loss landscapes, right, gradient descent tends to produce kind of wasteful movements, right, that are not in the direction of the optimal loss, and this can get you into situations that produce very long convergence times under gradient descent. So a typical solution that people propose is if they say, look, the problem is that the loss landscape in a discrete movement in this place isn't like first order information is not enough to avoid a wasteful gradient step in this case, right? Then the solution that a lot of people look to is second order methods, right? So I can sort of correct the motion and move directly towards the minimum. If I have access to the Hessian, or some second order information that will help me actually figure out which direction to go in. So that's sort of the second order picture. So here's our algorithm in contrast, right? So what we do is we intersperse gradient descent steps with occasionally applying a symmetry of the parameter space. So here, notice these lines are level curves of the loss. So we can apply some symmetry that gives us new parameters. Those new parameters have the same value of loss, so we haven't lost any ground in our optimization. But because that doesn't necessarily preserve the gradient, I can do this in a way which is going to increase the gradient and hopefully in this step and in next steps, and get me to the minimum faster. Okay, so here is the example of the group action that we consider in this space. So I have to highlight two things here. One is I'm using a weaker definition of parameter space symmetry than I did in the first slide. So I am not assuming that the action is linear. So earlier I said we're multiplying by a matrix when the group acts. Here I have a nonlinear group action. So this is the definition of the group action. And you can notice that the nonlinearity that you chose actually appears in the group action. Okay, the second thing is that this group action does not leave the model invariant. So it is data or batch dependent. It doesn't alter the data. I don't need to perform any transformations in data space, but it does depend on the data. So that what I get is an invariant loss function given data, and I also get invariant outputs given the data X. So that is weaker than you would want, but it's still useful. And the last condition here is the only really thing that we're asserting about the nonlinearity is because I need to invert the nonlinearity in order to have this action cancel and preserve the loss function, I need to assume the nonlinearity is invertible. So my typical example there would be something like leaky ReLU, where instead of flattening out on the negative side, it still has some slope. Okay, and so I get this group action here. And another issue is you do need to, so these H's, this is the data appearing in the group action. So I said the group action depends on the data, right? And here it's sort of defined recursively. And I need to take the pseudo inverse of these rectangular matrices. So I need to assume that I have enough data samples in order to compute this pseudo inverse with respect to my data. Okay, so if I do that though, so if I do all this stuff, what I end up with is a group action by n invertible matrices. So I'm removing this orthogonality condition, which was the condition that I needed for gradient descent and the symmetry to commute. And the point is that's actually a good thing, because if I didn't have that, then doing this group action wouldn't change the gradient, and I wouldn't have a hope of actually improving the optimization dynamics. Okay, so here's our very simple algorithm, which we call teleportation, after a paper of Armenta Iordan, which I should have a citation to them here, because they proposed the name, and they also proposed originally the idea to try to perform these symmetries in the parameter space to accelerate convergence. This algorithm is different than theirs, though. They just do random transformations, and they also are considering ReLU networks. So it's the symmetry action that we saw in the very first example. Here we have n by n invertible matrices. So the idea is basically simple. So basically every, say, k steps, or according to whatever schedule you specify, we're going to stop doing gradient descent. We're going to look at the model parameters. We are going to look at all of the symmetries in the parameter space. We're going to try transforming to different locations to see if we can find a larger value of the gradient with respect to this group action. In practice, this argmax is going to be probably going to be done by simply choosing some distribution over the group G and sampling some elements G and just trying to find, so you've set some hyperparameter, like we'll sample 100 elements. We'll see if we find a bigger gradient. And if we do, then we'll apply that transformation and move to those parameter values. And then we continue with gradient descent. So here are some empirical results about how that works. So for example, here in this slide, the blue line is a standard gradient descent. And the green line is given by Adagrad, which is a, Adagrad is a, you can think of, it's a second order method. So it attempts to use some approximation or diagonalized version of the Hessian to accelerate convergence. And so what our method does when added to either Adagrad or to vanilla gradient descent is it produces this orange and red line, which are going to lower the loss much faster, right? So over here on this plot C, right, you can see that with respect to the loss, right, our transformed models are achieving larger values of the magnitude. This would be the magnitude of the gradient, right? So they're increasing the size of the gradient as you go. Okay, and then I will end on this proposition, which is in our paper, which I think is kind of cool. So, so basically what it says is that if I have a large enough set of parameter space symmetries such that I can actually assure that my teleportation has taken me to a local maximum in the size of the gradient, then in that case, the gradient step I am taking is now in the same direction as if I were to have used a second order method, like Newton's method. So in other words, this sort of like dichotomy, right, between if I was at this point in my parameter space where gradient descent tells me to move this way, but the second order method tells me to move this way, after teleportation, those two directions agree. So that's one way to think about teleportation, is I'm moving to a place where gradient descent is the correct motion with respect to a second order method. Okay, so that's the end of my